Okay, so this podcast right here is going to go over Coulomb's law and the three different types of intermolecular forces that we learned in class. The first thing I want to go over is Coulomb's law. So what Coulomb's law says is that the more charge there is, the more attraction that the ions are going to experience. So if you look at this picture right here, you have a bunch of sodiums and you have a bunch of chlorine ions. So if this is positive 1, let's say, and this is negative 1, these particles right here are going to attract. But let's say one of the particles ends up being plus 2 and the other one ends up being negative 2. Then these particles right here have a larger charge, and so they're going to attract even more. So if we look at this formula that I'm going to introduce to you right now, the F stands for attractive force, so the force of attraction. You could even put a little a here if you want, and it's equal to Q plus and Q minus, so opposite charges attract, right? In ionic solids. So, and it makes sense because if the charge increases, if you increase the numerator, then the answer is also going to go up. So this makes sense mathematically. The more charge there is, the more force it's going to have. But then if we look at the distance, we said if you have a larger distance between the particles, then that is going to cause the attraction to decrease. It's like saying, hey, you have two magnets. If they're very far apart, if the magnets are very far apart, they're not going to have much attraction. Okay, there isn't much attraction. But if they're very, very close, then you're going to see a very large attraction. So the opposite is true. So if you increase the distance, the denominator in this case, then this number is going to go down. So the larger the distance, the smaller the attractive force, or the smaller the distance, so the things are closer together, then the larger the attractive force will become. And that is exactly what Coulomb's law says. And we went over this already with this example, where here you have two anions, and the distance between water and these anions is the same. The distance is the same. So we can't look at d squared. We can't use distance to tell us whether something's going to attract or not. So instead what we look at is the charge. Negative 1, negative 2. Negative 2 has a larger charge. So that is why this guy experiences a larger attraction, because it has a larger charge. So that's going to be your explanation for that. Now, for this particular podcast, I want to emphasize intermolecular forces. We learned that difference between chemical bonds and intermolecular forces. Chemical bonds hold atoms together to form molecules. So, for example, in water, the hydrogen and the oxygen are connected through a bond. They're held together. Okay, it is this very, very strong bond. It's called the polar covalent bond. But between individual molecules, you could have attractions, not bonds, but attractions, very weak attractions. And these are called our intermolecular forces. So here, there's a bond, but there could be an attractive force right between these water molecules. So that's what we're going to learn about. These water molecules right here and these hydrochloric molecules right here. But we also talked about this, where I told you that these little dashes represent attractions, and the bonds connect individual atoms within the molecule. So make sure you know the difference. Intermolecular forces, they are not as strong as ionic and covalent bonds, but they are very important. Intermolecular forces do determine whether something will form a solid, a liquid, or a gas. So if a substance has very strong intermolecular forces, then you're going to tend to see a solid. And if a substance has very weak intermolecular forces, for example, our gases, such as methane and hydrogen and octane and all these different gases that we see around us, they are in the gas state at room temperature because they have weak intermolecular forces. And if something has a very, very strong intermolecular force, then it's going to require a lot of heat in order for it to boil or in order for it to melt. So when we see substances that are solid at room temperature or even at high temperatures, it's because they have very strong intermolecular forces. If they vaporize very quickly, meaning that they're highly volatile, then they're going to have very weak intermolecular forces. So here I mentioned that London dispersion is the weakest. Then we have dipole-dipole, which occurs between polar substances, and then hydrogen bond, which is very similar to a dipole-dipole, but it's considered to be stronger because it involves a very weak electronegative hydrogen and a very, very, very strong electronegative halogen, such as fluorine or oxygen or nitrogen. Okay, so fluorine is the halogen, oxygen is not, but it is considered to be the second most electronegative atom, and then the third one would be nitrogen. So the way I memorized it is hydrogen bonds like to have fun. So hydrogen bonds occur between fluorine, oxygen, and nitrogen, F, O, and N. So the first one I want to go over is London dispersion. London dispersion is the weakest of all three. And even though they occur between non-polar substances, they do experience a temporary partial dipole. So the way this works is, I'm going to draw it here for you, and you fill it in your notes as well. Here, let's say we have xenon. Okay, let's say we have xenon, it's a gas. And we know that these atoms have electrons, and they're moving randomly inside the atom. And sometimes the electrons are going to be on this side and not on this other side. And so we say that there's going to be a partial negative charge on this side. And it's temporary, okay, meaning it's not always going to be there. And then the other side, on the other side, it's going to be partially positive. And again, these electrons are going to eventually shift in the other direction, and this is going to become partially negative, and then this is going to become partially positive. So it's constantly changing, like a water balloon. You guys know it shifts in one direction and then the other direction when we're holding it. That's the same way these London dispersion forces occur. Because of these temporary charges, they're going to form attractions to other substances as well that are not polar. And so if we have multiple of these, for example here, let's say we have xenon here, and then there's a lot of these electrons there, and zoom out. Let me actually start over. So let's say we have our xenon here, and we have all these electrons right here. Okay, so these are going to be partially negative. And let's say you have another xenon, and the electrons are here, then this side's going to be partially negative, this side's going to be partially positive. And so there's going to be an attraction here between this partial negative and this partial positive. This attraction is a London dispersion force, and it is very, very weak. Okay, so it says here, when electrons happen to momentarily move to one side of a molecule, it creates a temporary partial charge. When a neighboring atom comes in, they attract. So that's exactly what I just drew. So this is called London dispersion force. The other one is, the second one is called the dipole-dipole. So the way the dipole-dipole works is that it occurs between polar molecules. So here, if we look here, here's chlorine. It has a partial negative charge, and it's not temporary, it's actually permanent. And this partial positive here in chlorine, these partial charges occur because there's a difference in electronegativity. And so the partial positive hydrogen is going to attract to the partial negative of chlorine. And these interactions here are called dipole-dipole forces or dipole-dipole interactions. So here's a closer look. This right here is a covalent bond, but because of these partial charges, there's going to be an attraction here, and this attraction is called the dipole-dipole. The reason this is not a hydrogen bond is because the hydrogen is connected to chlorine, not fluorine, not oxygen, and not nitrogen. So whenever you do have oxygen or nitrogen or even fluorine, it's no longer called a dipole-dipole, it's called a hydrogen bond because it's stronger. So it says here, it's like a dipole-dipole force, but it's stronger because it involves hydrogen and one of these highly electronegative atoms. And they occur between polar molecules. This is why water striders, which are little insects, this is why they sit on water. They could walk on water because the hydrogen bonds in water are very strong. And because the hydrogen bonds are strong, water takes a while for it to boil. So anything that has very strong intermolecular forces will require a lot of heat, a lot of energy in order for it to boil. Here's an example of methanol in water. So here's methanol. It has a hydrogen. It's partially positive in comparison to oxygen. And here is a water molecule that has a partial negative. So the partial negative and the partial positive, they're going to attract here. So this is a hydrogen bond because it's part of fun and it has an attraction to hydrogen. Here are two methanols, and that could also create a hydrogen bond. It doesn't always have to involve water. It could be anything that is polar, yet it has hydrogen and it's attracted to another oxygen, fluorine, or nitrogen. Here is DNA. DNA, if you look into the nucleotides of a DNA structure, you could see that one strand is connected to another strand through hydrogen bonds. So if you look here, this nitrogen is polar. It's going to have a partial negative charge, and it's going to attract to this partial positive hydrogen. So this right here is a hydrogen bond, and this is a hydrogen bond. Again, it's part of fun. Nitrogen, oxygen, oxygen, nitrogen, oxygen. So these are good examples of hydrogen bonds that connect our DNA together. And that is all for this lesson on intermolecular forces. I know it's a little difficult to understand, so by doing the problems and looking through your notes, I hope you are able to get an understanding of how particles interact with one another, whether they're nonpolar or whether they're polar or whether they're very polar, because of this fluorine, oxygen, and nitrogen that exists among hydrogen bonds.